All right, let's take a look at section 4.6. Okay, first thing, before we get into too much, I just want to make sure everybody remembers what isosceles means. Okay, so a triangle is isosceles if it has at least two congruent sides. Based on that definition, what else would have to be isosceles? What other kind of triangle? It says it's isosceles if it has at least two congruent sides, yeah? Right, based on that, equilateral would be considered isosceles. It does have at least two congruent sides. But if we're talking specifically about an isosceles that has exactly two congruent sides, just two, does anybody remember the names of those sides? The two congruent sides in an isosceles triangle are called something, and then the one on the bottom is something else.
The legs and the base.
Yep. The two congruent sides are the legs. And the side that's not congruent, that's your base. Okay, it's just a quick refresher about that definition. The two angles that are adjacent to the base, those are called your base angles. Anybody remember the name of the angle that's by itself? Not the base angle, but it's the vertex. Yep, the vertex angle. Yeah, the vertex angle is the angle that is opposite the base. Okay, and there's a quick picture of an isosceles triangle. So the bottom side is the base, two congruent sides are the legs, the base angles are at the bottom, vertex angle is up at the top. Okay, any questions on that? All right, so we're going to look at a theorem, okay, having to do with isosceles triangles. It's called the base angles theorem. Okay, so I've mentioned before, there's a relationship between sides that are congruent and the angles across from those sides. Anybody know what happens if you've got two sides that are congruent in a triangle? What about the angles across from those sides? Yeah?
They're congruent.
They're also congruent. Yeah. All right, so kind of a formal way to say that, if two sides of a triangle congruent, then the angles opposite those sides are congruent. Okay, so basically what that means is in a triangle, however many sides are the same length, that's how many angles are the same measure. Three sides the same length, three angles the same measure. Two sides the same length, two angles the same measure. If all the sides are different, all the angles are different. Okay, and we can also look at that in reverse. Okay, we can look at the converse of that. So the converse is when you take the if and the then, you switch it. So instead of starting with two sides being congruent, then the angles being congruent, we're going to switch it around. If you've got two angles that are congruent, then the sides opposite are congruent. Okay, so if two angles in a triangle congruent, then the sides opposite those angles are congruent. So when we do a proof, if we use one of those theorems, we just got to try to remember which one is the theorem and then which one is the converse of the theorem. So the theorem is used to prove angles are congruent. The converse is used to prove sides are congruent. So you just have to remember that. Okay, and if you're looking in the book, these two theorems are, they're both on page 236. They are theorem 4.6 and 4.7, but again, I wouldn't be expecting that you would know that. You don't need the theorem number. Everyone have the theorems? All right, so since these are theorems, are they something we have to prove or something we can just assume they're true? Yeah, we have to prove them. Okay, we probably won't go through both, but let's just prove the base angles theorem. All right, so we're given that this shape is a triangle, and they tell us that AB is congruent to AC. Let's mark that. AB, AC. We have to prove that angles B and C are the same. That's what the base angles theorem says. Angle B and C are congruent. Any thought what we're going to have to do here? We've had to do this kind of thing before. The way the diagram is right now, we don't quite have enough information to do it. We got to kind of add a little bit to it. I don't have a thought what we could add to that diagram. So generally, think about if you're going to prove angles are congruent, first you want to prove triangles are congruent. Right? Notice I said triangles. We only have a triangle there. There's only one. So maybe we could draw something that would cause there to be two triangles instead of one. Any thoughts on how we do that? Yeah.
Triangle bisector.
Okay, we do want to draw in a bisector, a specific type of bisector. So we have segment bisectors and we have angle bisectors. Anyone have a thought which one we want to draw here and from which letter you'd want to draw it from? You don't want to mess up angle B and C too much, so you probably wouldn't want to draw something that's going to cut B or C into pieces. Yeah?
Bisect angle A.
Yeah, let's construct that first. Okay? Or you could write down the given first, either way. Since we've normally done the given, let's write the given, then we'll write what Marquise just said. AB is congruent to AC. That's given. All right, statement 2. That's going to be just a draw statement, okay? Because we're allowed to, we know how to bisect an angle. We've done that with a construction. So that's something appropriate you're allowed to do. So draw, let's see how they word it. Draw the bisector of angle CAB. The reason why you can do that, it's a construction. Okay? Bisecting an angle. Okay, I think these kinds of proofs, they're the hardest ones. When you have to draw something that's not there, sometimes it's a little tricky to know to do that. But it really is the only way to do it. So let's draw that in. Draw in your angle bisector, just like that. Do you have to label a point? Sure. We might need that. There's no reason to write you don't have to do a statement and reason for that. You could just label that point. Okay, so where the angle bisector hits the segment BC, I called it D. Okay, now step 3. Since we just bisected angle CAB, what can we say now? We just created a couple angles here that are congruent. Yep?
Well, you could say AD is congruent to AD.
Okay, we could also do that. We're going to have to do that eventually. And what's the reason for that? That's reflexive. All right, so now we've got a side, we've got a side. What else do we have?
Right angle.
We don't know that it's a right angle. It could be that this line isn't exactly vertical and that one's not perfectly horizontal. We don't know for sure. But we do have something else we know that is congruent because of what we sketched. Yep?
The D is the point of segment BC. Because if it's possible, that's not.
Yeah, that's an angle. Once we prove these triangles are congruent, which they will be in a second, then we could prove D is the midpoint because BD and CD are the same length.
Couldn't you construct a perpendicular line to make it a right angle?
I could have. If we had done that construction, maybe, yeah, we could have proved it a little differently. But the way we drew it, we decided to draw it as an angle bisector. But yep, we could have constructed it a little differently and said maybe it's an altitude, which means it comes straight down perpendicular to the base. Yeah.
Angle BAD and angle CAD are bisected.
Right, so angle, let's see, yep, BAD and which one?
CAD.
Yep, angle CAD are congruent. And the reason? That goes back to our construction in step 2. I put step 2 just in case we had another construction we wanted to reference. In the reason, we'd know which one we're talking about. Okay. So now our 5th step, I think we've proven the triangles are congruent. Okay. So I'll start with the top one. That's congruent to that. And then I want someone to see if they can give me the letters in the bottom one. So let's do triangle BAD. What would the letters have to be for the bottom one? If I said B, then A, then D. Yep. Yep, CAD. Good. What's the reason why those triangles are congruent? What theorem did we use? Marquise?
Side angle side.
Good. Side angle side. And now our last step, we've proven the triangle's congruent. Anybody remember why B and C would have to be the same? They are now. Yeah, go ahead, Mike.
CPCTC.
Very good. Once you prove triangles congruent, all their corresponding parts are congruent. Right? So angle B is congruent to angle C. Reason? Exactly what Brian just said. CPCTC. Right? So now we've proven the base angles theorem. Any question on that proof? Okay, we're not going to be focusing on a lot of proofs today like we did last week. Pretty much every section was proofs. We are going to have some more calculations. There will probably be at least 1 or 2 more proofs, but we'll do some calculations too. Okay, so equilateral triangle. Okay, that's a special kind of isosceles triangle where you have all 3 sides that are the same. So what is that going to mean? Based on the theorem that we just looked at, if all 3 sides are the same, what would the base angles theorem tell you? Yeah?
All the angles are the same.
All the angles are the same. Because we just said if all the sides are congruent, the angles opposite those sides are congruent. Well, if all the sides are congruent, all the angles are congruent. We had a name for a triangle with all angles the same. It was equiangular. So if a triangle is equilateral, it's automatically equiangular. I think we said that before, but we never really proved it. We just said it. Okay, now we proved it using the base angles theorem. Okay, so remember, these are corollaries. Okay, a corollary is still something you would have to prove, but it's too similar to another theorem to be deserved to call a theorem. Okay, so a corollary is a statement that's very, very similar to a theorem. And it's so similar to the base angles theorem, this doesn't deserve to be called a theorem. Just like a small addition to the base angles theorem, it's actually just a special case of the base angles theorem. That's all it is. All right, but we'll use those two corollaries. We'll do some arithmetic now. Do some calculations. Any questions on those? All right. So let's try a couple problems here. Right, so find the value. We'll do x, and then we'll also do y. Hey, anybody think they know the value of x? And you do have to look at those markings, because without those markings, you couldn't do it. But those help us a lot. Yeah, anybody think they know it? Or, and I'm going to ask you, how do you know that? Yeah, Denver?
60.
Yeah, x is 60 degrees. Well, x is 60. How do you know that? Okay, all the sides are equal, which makes it what kind of triangle? Equilateral, and it also automatically makes it equiangular. And what does that mean? If all the angles are equal, why does it have to be 60? Right, you have to add up to 180. That's the key right there. So three numbers, all the same, 60, 60, 60, and they add up to 180. All right, so x is 60. Let's find y. I don't think they could tell me what y is. Might be a couple different ways to think it through. Yeah.
Well, first I would draw in 60 degrees and then on each angle.
Okay, so yeah, we could fill in. That's a 60, 60, 60. Yep.
And then that angle bisector.
This.
Yeah, that line on the opposite side of the top 60 is 120 because it's on a straight line.
Okay, so that's going to give me a 120. Now keep in mind, we don't know, I'm just going to erase this in a second, but this line right here, we don't know that that's an angle bisector. If that comes out to 60 and 60 on each side of it, then it is, but I don't think this can come out to 60 because of what you just said. But let's keep going.
It's a segment bisector.
It is, yep, it's definitely a segment bisector. Okay, now how do we get y from that? So far everything he did is good.
Y is 20 because the two congruent sides have congruent angles, and the two congruent angles would have to be well, it would be 40 and then divided by 2.
Okay, so everything he said is pretty good. He said that you get an isosceles triangle. This is 120. Because it's isosceles, the base angles are the same. And you said they were both 20?
Yeah.
Okay, so if we added 20,
Actually, my bad.
20 and 20 and 120 wouldn't quite add up. So think about, what do you have left after you do 180 minus 120? Yeah, they're each 30. That's 30, and that's 30. Okay? Because when you take 180 minus 120, you're left with 60, and it has to be split equally in an isosceles triangle. So y is 30. So now if we take a look back at that line that I had shaded in red, it definitely is not an angle bisector, but it is a segment bisector. Yep. But the way the picture's drawn, it almost does look like, it could be close to an angle bisector. So you got to kind of go by the calculation, not how the picture looks. All right, why don't you try that one on your own. See if you can find x and then find y. It might be easier to find one before the other. That's up to you. But see if you can find x and then find y. Okay, so they've asked us to find x and y. Okay, anybody find, let's start off with, maybe, which one is easier to start off with here?
Y.
Yeah, you could get y first. Okay, what's y going to be?
63.
Yeah, it's an isosceles triangle. 63 and y are the base angles. They have to be the same. So y is 63. And then the degree symbol was already on y. That's why I didn't put it. Okay, what about x? Now that we know y is 63. Alyssa, how can you get x? Okay, add them up. Yeah, you get 126. Yeah, subtract that from 180, and what do you get? 54? Yep. Right, so we get x equals 54. Okay, so again, this section will be a mixture of kind of some calculations and some proofs. Okay, a little bit of both. Any questions on that? All right, so we're going to take a look in the last part here, just specifically at theorems that have to do with right triangles. Okay, so remember, in a right triangle, we don't have a base like we do in an isosceles triangle. We have a hypotenuse. Okay, the two sides that are the shorter sides, we call those the legs, and the hypotenuse, that's the long side. Hypotenuse is always across from the 90. Anybody tell me why the hypotenuse would have to be the biggest side? Based on what we know about, anyone know why? Yeah?
It's a diagonal.
Well, why can't one of the legs be bigger?
Well, if one of the legs was bigger, then the hypotenuse would be even more bigger because it's a diagonal.
Okay. How about in terms of like an angle? Anybody know what the connection is between the length of a side and the size of an angle? There's a connection there between angle size and length of the side. Yeah.
Isn't it? It's a right angle, and you have the measurements of both the legs. Then, then like if it's a right angle, you have know the measurement of the hypotenuse because there's only so much room you have between the legs and the other leg.
Yeah, you can. If you know the two legs, you can definitely get the hypotenuse. There's a theorem that does that. So my thought here with the hypotenuse is that the biggest side is always across from the biggest angle. And we don't know that yet, but that's the idea. Biggest side is across from biggest angle. Smallest side is always across from the smallest angle in a triangle. Well, if you've got a 90, I guarantee you the other two angles in a right triangle, they can't be bigger than 90. So since 90 is the biggest angle, what's across from it has to be the biggest side. And that's why the hypotenuse is the biggest. So up to right now, we've got 4 ways to prove triangles are congruent. Anybody remember what's one of the 4 ways we have? Yeah, Connor?
Angle, side angle.
Okay, angle, side angle. Yep, that's one.
Angle, side.
Side angle, side. Okay, anybody remember, give me another one? Yep.
Angle, side.
Yep, angle, angle, side. Angle.
Side, angle, angle.
Side, that's the same as this one. Yeah, side angle, 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 side. But there's one more. Yeah.
Side, side, side.
Yep, side, side, side. So those are the 4 ways we've got so far. And you can use any of those 4 ways on a right triangle or isosceles. Okay? These 4 methods of proving congruence, they work on any triangle. But we're going to learn a 5th way. And the 5th way is a method special for right triangles. Okay, it's something you can only do if you have a right triangle. And it's called the Hypotenuse Leg Theorem. Okay, what we'll do when you're writing this as a reason and a proof, you can just put HL theorem, hypotenuse leg theorem. Okay, and this is on page 238. In the hypotenuse leg theorem, it says that if you've got a hypotenuse and a leg in one right triangle that are congruent to a hypotenuse and a leg in a different right triangle, then the triangles are congruent. Okay, so if you've got two right triangles and the hypotenuses are congruent and then a leg is congruent, the triangles are automatically congruent. Let's go like this. So let's see if that would normally work. Okay, let's see if that fits into one of these other four. If this is really just a repeat of something else. Okay, so let's sketch two right triangles. And let's mark what it says. Okay, you got a hypotenuse in one, matching a hypotenuse in the other. That's a 90. That's a 90. And you've got a leg. Doesn't matter which leg. Pick either one. So you've got two sides and an angle. Does that fit into one of the four reasons we already have, or is this something different? Yeah, this is not one of the four we had before. Okay? So to be polite, I'm going to write it the nice way. You've got a side matching a side. You've got another side matching another side, and an angle matching an angle. That's not one of the four ways we proved that works. But in a right triangle, it does. Okay? And the reason why it works is because of what somebody said earlier. If you have two sides in a right triangle, you can find the third side using the Pythagorean theorem. That's the name of the theorem. I didn't say it earlier. But you can prove with that theorem that if two sides match, the third sides are automatically going to match. So really, the reason the hypotenuse leg theorem works is because of the Pythagorean theorem. And the Pythagorean theorem would give you side, side, side. That's one reason why the hypotenuse leg theorem works. Any question on that? Right now, you don't have to know the Pythagorean theorem yet. Okay, we're not going to be using it to do anything. But does anybody already know what it is? The Pythagorean theorem? Yeah, Morgan? Anybody remember I mean, we usually use three letters. You can use any letters you want, really. It doesn't matter.
A squared plus B squared equals C squared.
Yeah, A squared. What's A? What's a B? What's C? What is that?
A is a leg, B is a leg, and C is a hypotenuse.
Yep. So the idea of the Pythagorean theorem is that if you take one leg, you square it, take the other leg and square it, and then add them, it's equal to the hypotenuse squared. Whether you use x, y, z, or a, b, c, it doesn't matter. Right, but that's the Pythagorean theorem. And that only works with a right triangle. There are formulas we can use that work with non-right triangles. We won't really study them this year, but if you take trig, we do study them. We'll look at those a little bit. All right, so this diagram, this is on page 238. Okay, what basically I tried to draw here is AE. That's like an antenna that's in the ground. And then there's three wires coming down from the top of the antenna. Okay, AB is kind of going in the back, AD is going off to the left, and then AC is coming out towards the front. Okay. Any question on the picture? Okay, so it's just an antenna that's being held to the ground. And they give us a little bit of information. They say that the antenna, okay, which is AE, is perpendicular to EB. Okay, that's running, EB is right along the ground. And then the antenna is also perpendicular to EC. Okay, I tried to mark that. And the antenna is also perpendicular to ED. So how many triangles do we have in that picture? 3, and they're all what kind of triangle? They're all right triangles, so we can use some of the theorems we just learned. Okay. In addition to knowing that, we know that AB is congruent to AC, which is congruent to AD. What are those segments? I mean, they're the wires that are holding the antenna, but in terms of the triangle, AB, AC, and AD are like your what? They're your hypotenuse. Yep. They're your hypotenuse. Okay, so, whoops.
Whoa.
So what I want to do is prove that basically the 3 triangles we have in that picture are congruent. Okay, what we'll do is we'll focus just on the first 2, because if you can get the first 2, the third one, it's just more of a repetition of the first 2. Okay, so why don't you try that one on your own? See if you can show that triangle AEB, which is the one that goes kind of towards the back, and AEC, which is the one coming towards us. Show that those 2 triangles are congruent. Okay. And again, if you could do those 2, the third one, you're just repeating some of the stuff you're going to say for the first 2. And since they are right triangles, keep in mind any new theorems that we have that you're allowed to use now. Okay. So give that a try. All right, what would be first thing that we could say if we want to prove triangle AEB and triangle AEC are congruent? We have some extra information here that we might not use in the proof because we're not doing the third part of the proof. Just the first 2 triangles. So what could I say first? Yeah, Luke?
Line AB is congruent to line AC.
AB is congruent to AC. Yep, that's good. And exactly, that's given. Okay. Yep, so we got AE congruent to AE, that's congruent to itself, that's the reflexive property. So we've got 2 sides. And if you're going to use the hypotenuse leg theorem, which kind of looks like the direction we're going in, you have to make sure you say that you have right triangles. If you don't say you have a right triangle, then that theorem doesn't apply. So that's probably the next thing we should say. Triangle AEB and triangle AEC are right triangles. Okay, the reason, that's the definition of a right triangle. Yeah?
If we say that the hypotenuse leg theorem is SSA, we get that on the test.
Yeah, because SSA is not a, it's not a congruence postulate. SSA never works. Okay, so make sure that if you're going to use hypotenuse leg theorem, write HL theorem. All right, so step 3. These are right triangles. Why? That's the definition of a right triangle. Okay, you have a right angle that was given, okay, because of the perpendicular sides. Now, way back when we started proofs, what we might have done here is we'd say, okay, since AE is perpendicular to EB, it forms a right angle by definition. Because it's a right angle, then it's a 90-degree angle because of the definition of a right angle. We'd kind of go through that extra step. But that's okay at this point. Okay, if you've got two lines that are perpendicular, we know that it makes a right angle, which means it's a 90. That's fine. Okay. So do we have enough information? Do we have a hypotenuse and a leg? Have we done both? We got AD and AC. Okay. That's a hypotenuse. AE, that's a leg. And we got right triangles. So yes, we can use the hypotenuse leg theorem. So that's your last step. Triangle AEB is congruent to AEC. Reason? HL theorem. Again, don't ever put SSA because that's not a congruence postulate. Okay. Any question on that proof? Okay, let's look at this one. Okay, I just want you to look at it for a second. And it asks us if we have enough information to prove those triangles congruent. Okay, and remember, you can't go by how it looks. You've got to go by what's actually marked. Okay, how about Nick? What do you think?
Yeah.
Okay, go ahead. Tell me what you know that's congruent here.
Line BA and BA.
Go ahead. Yeah, BA, segment BA, and which other segment?
DA.
DA. Okay. So that's given. We've got a side. Anything else that's congruent? So BC and DC are not marked. We don't know if they're congruent. But so you think we can prove these triangles are congruent still, right?
Yeah.
Okay, then we need more information. We can't do it with just a side. Let's just see if there's anything else. Yep, you think?
290 angles.
Okay, they look like 90s, but are they marked? Yeah, they're not marked as 90, so we don't know. It could be like 89 and one's 91. They could be very close. Like, let's just see if we can at least name something else that's congruent, and then we can decide if we have enough information. Yeah?
Line CA is congruent to line CA.
Sure. CA is congruent to CA. That's reflexive. But we still don't have enough right there. Okay?
It is possible. Yes, it is, because if we have those two congruent, those legs, then the base, angle D and angle B are congruent, because it's an isosceles triangle.
Angle, which one's angle D?
Take out CA, the second CA, and since we have DA and BA are congruent, then by definition of an isosceles triangle, angle D and angle B are congruent.
Okay, let's take a look at that. So if you look at the big triangle, triangle ABD, okay? I think what you said is true. That angle is congruent to that angle. But now we've got two sides and an angle. Is that enough?
Yeah.
That works. What postulate would that be? Side angle. Is that one of them? Side. If it was side angle side, if we knew this angle, we don't know if it's a right triangle. Absolutely. So, is that a congruence postulate? Side angle. No. Okay, remember, if you write it the other way, it's not nice. Okay, that's not a congruence postulate. So no, we don't have enough information here. If we knew that we had a right angle, then we could do it. If we knew angle BAC and DAC, then we could do it. Or if we knew segment CB and CD were congruent, we could do it. But we don't know any of those. So, nope. We do not have enough information to prove it. Okay. We don't have enough. All right, so our last one we'll do is just a calculation to find x and y. Okay, let's start out with x. What is x going to be? Look at the kind of triangle that it's in. Yeah.
It's going to be 60.
Yeah, it's 60.
Why is it going to be 60?
So we know x is 60. What else are they telling us here? We've got to be careful that you don't miss this. It's almost kind of hidden, but it is labeled in the diagram. Yep?
We have parallel lines.
Yeah, we have parallel lines. Okay? Without the parallel lines, you'd be done at this point. There's nothing else you can do. But because we have two parallel lines cut by a transversal, we know all kinds of things. This angle is the same as that angle. We could do it the other way. Two parallel lines cut by a transversal. This angle is the same as that angle.
Then we have, since 60 is there, it's 60 and 60 on the other side.
So you said, yeah, we've got 60,
60.
60, and yep, that's a 60.
But then we have 60 on the opposite side because if it's
What's the opposite side?
meeting below x, those two there are 60 because 6, 12, 18, 180 because it's up.
Now, why do they both have to be like 60 and 60? Why not 70 and 50? Because these aren't marked as congruent. So we'll look at that in a second. So if we look at it, we got some angles that are matching up. Anybody know why? These are end up going to be 60s, but anybody see why?
Because we have one that's congruent. That 60 in the top right corner
Yeah?
is congruent to 60.
There you go. Yep. So now you had the 60 up here, which matches the 60 down here. And now you've got a straight line on the bottom. So we've got 60, 60, straight angle makes 180. That has to be a 60. And that's what helps us do the other triangle. If the one at the bottom is 60 and the one at the top is congruent, it also has to be 60.
I don't think that's marked right.
Which one?
Because you marked two of the same.
Oh, yeah, okay, I got you. Yeah, so this one would match, you're saying that one?
Yeah.
Yeah, that's how it should be marked. But
And
either
that should not
way,
be 60 because,
we get 60s.
no, not the top. The top of that one, the isosceles triangle. That should not be 60 on top.
This one?
Yeah.
Well, you agree that this one and this one have to match, right?
Right, but you have another one marked. You have another 60 marked.
I have another, well, let's just look at the numbers for now. You got a 60 here and a 60 here, right? And then this angle,
That would be 60.
that has to be 60, right? If that's 60 and then that's 60, that forces the top one to be 60. So everything there, it turns out you have 3 equilateral triangles. So y is also 60. Okay, it is a little tricky to look at, but because of the parallel lines, that's what helps us out. Okay? All right, so for tonight, on 239, do you look at just the odds on 9 through 25, and then 33, 36. And for the MCAS, just 1 through 6 on the multiple choice.